For today's deep ocean observing session, I wanted to talk a little bit about activities and recent developments at Seabird Scientific as they are relevant to ocean sites. I'm Jochen Klinke, Director of Science at Seabird Scientific. Most of you probably will not know me, so let me give you a quick introduction. I've been with Seabird just under 4 years now in my current role since the beginning of the year as Dave Murphy is transitioning into retirement. My background's in science, mostly instrument development, originally at Scripps Institution of Oceanography, and later commercializing the underway CTD technology at Ocean Science. I can think of at least 4 topics that are directly related to deep ocean observing within ocean sites. The first 2 are focused on evaluating new sensors and materials to achieve better accuracy and stability of pressure and conductivity measurements. This effort is done within the framework of Deep Argo in collaboration with Natalie Zilberman from Scripps. This project's really just getting underway, so there are no results to report yet. Today, I'm going to highlight 2 other activities at Seabird, and that first one is the drift analysis of microcats, and the second one is really the development of improved pH sensors for deep ocean observations. Let's first take a look at the drift analysis of microcats. That's work that's been done by Kim Martini, our physical oceanographer at Seabird. The goal here is really to determine the long-term stability of the SBE-37. She determined drift by looking at pre- and post-deployment calibrations and assuming that the rate of change is linear over the time span. It covered an enormous amount of data and over 20 years of manufacturing and included over 4,000 different sensors. You can see the results in the plots below, temperature on the left, conductivity in the middle, and salinity on the right. The vertical lines in the plots indicate the initial instrument specifications, and what you can see that there's really no bias in temperature, and over 90% of the temperature sensors maintain their accuracy within the initial specifications. There is a bias in salinity that is slightly fresh and is most likely caused by environmental fouling of the conductivity cell. The next steps here are really to look at the actual drift rates, and that's to be done soon. The second project I wanted to highlight is focused on improving our pH sensor technology. That effort's really driven by Charlie Brehm, our senior chemist at Seabird. We have Isfet sensor technology that's used in both our deep sea fox, which is really just a deep sea fed, and an SMP ODO 37, but also in the float pH for the Argo BGC floats. This is technology that was originally developed by Ken Johnson and Todd Martz and Honeywell. You can see an example of an Isfet sensor in the bottom right picture with a detailed view of the actual Isfet chip. Currently, that technology is rated to about 2,000 meters. It does require very involved nonlinear pressure and temperature characterization of the actual Isfet chip. And when you do that, you typically can achieve accuracies of about plus minus 50 millipH and a stability of a few millipH per year. But even with that characterization, you have large temperature and pressure offsets over the whole pressure range, and also a very nonlinear response of the sensor near the surface. So it's very difficult to model, and our yield in manufacturing as a result of that is actually quite low. So we've been looking at ways to minimize the effect of pressure on the actual Isfet signal, but also to reduce the calibration time. We recently submitted a patent for a pressure compensated design that removes the effect of pressure on the sensor. And what you can see is that the highly nonlinear response of a standard Isfet pH sensor gets completely linearized in this design. With that, we're able to extend the depth rating to about 4,000 meters. It reduces the calibration time, improves the yield, linearizes the calibration model, while actually increasing the accuracy by a factor of 3. So I think we're on the right track here. We hope that by looking at pressure compensating the actual reference as well, that we can potentially bring the sensor to full ocean depth. So I hope I was able to give you a little bit of an insight in terms of what's going on at Seabird. There's maybe two efforts I'd like to draw your attention to, looking a little bit further into the future. One is kind of focused on standardizing our cable and connectors and transitioning connectors to MCBH. The other one is development of our next generation software, where we really have just a single software for all of the Seabird instrumentation, able to use modern communication protocols and mobile devices. The focus here really is on much improved ease of use. With that, I'm looking forward to any questions you have in the panel discussion. Thank you.